Space is freezing. The vast empty vacuum between the stars hangs at about minus 270 degrees Celsius, just a few degrees above absolute zero. But somewhere much, much colder exists, and it's not out there among the galaxies. It's right here, built by human hands. Inside a small laboratory on the International Space Station and another in a research facility on the MIT campus, scientists have created temperatures colder than the vacuum of space itself. Colder than any temperature the universe naturally allows. They're doing it not to break records, but to watch reality itself slow down, stretch and blur, revealing the hidden, underlying rules of quantum physics. At this extreme cold, matter stops behaving like normal stuff and starts acting like a single massive wave. This is the story of how humanity built the coldest place in the universe, what it taught us about the fabric of everything, and how these alien states of matter could unlock the future of technology. Welcome to Cosmic Crunch. Prepare to be frozen. The meaning of absolute zero and the third law. Temperature as motion and energy. Temperature isn't about how cold something feels. It's a direct measure of kinetic energy, the energy of motion. Think of it this way: everything is vibrating. The air molecules, the atoms in your coffee mug, even the nucleus of a distant star. The faster these atoms move, vibrate or spin, the hotter they are. As you cool something down, you are literally siphoning energy or slowing down all the motion inside. Defining the limit, 0 Kelvin. Absolute zero, or 0 Kelvin, is the theoretical finish line, the point where all atomic motion completely stops. That's minus 273.15 degrees Celsius. At this point, there is no vibration, no energy, and no heat, just perfect stillness. The universe, in its coldest, emptiest reaches, can only get down to about 3 Kelvin, the residual warmth left over from the Big Bang, known as the cosmic microwave background. This energy constantly bathes everything in space, setting a natural floor. The third law's barrier. But here's the catch, and it's dictated by the third law of thermodynamics. Absolute zero is physically unreachable. The law states that as a system approaches absolute zero, the processes of cooling slow down exponentially. Essentially, you can never fully remove the last bit of energy because the remaining energy is needed to facilitate the cooling process itself. It's like trying to perfectly catch a shadow. The closer you get, the harder it becomes to cool further. However, scientists can get incredibly closer than the universe does, within billionths of a degree. And at that scale, the weirdness begins. Why go so cold? The quantum realm unveiled. Breaking Newton's rules, matter as a wave. When you cool atoms to near absolute zero, the everyday classical rules of physics break down. Atoms stop obeying the predictable mechanics of Newton and start obeying quantum mechanics. This happens because cooling increases an atom's de Broglie wavelength. It expands its wave-like nature. Normally, this wave is too small to notice, but as the atoms slow down, the wave stretches, and the atom stops behaving like a tiny particle and starts behaving like a smeared-out wave. The birth of the Bose-Einstein condensate. The most incredible thing happens when matter reaches a critical temperature, typically measured in nanokelvin, or billionths of a degree above absolute zero. The atom's individual de Broglie wavelengths overlap and merge into one shared quantum state. This is a Bose-Einstein condensate, or BEC. Think of it as atoms syncing up, behaving like one gigantic, flawless superatom. Their individual identities vanish, and they share a single unified quantum function. It's the highest possible level of order. Alien properties of matter. The resulting BEC shows bizarre alien properties. It can flow without viscosity or friction, a superfluid. If you stirred it, it would spin forever. It can exhibit superconductivity, conducting electricity with zero loss. It can seemingly exist in multiple places at once, displaying macroscopic quantum coherence. By freezing the universe, physicists are gaining access to the fundamental operating system of reality, where matter itself becomes one perfect, coherent wave. Part 3. The Cold Atom Lab and the Power of Microgravity. Building the coldest spot in the universe. In 2018, NASA launched the Cold Atom Lab, or CAL. It's about the size of a mini-fridge, mounted inside the International Space Station. Why go to space? Up there, away from the constant subtle pull of Earth's gravity, atoms don't settle, they float freely. On Earth, BECs quickly collapse or sink due to gravity, giving scientists only milliseconds to observe them. In space, the condensate remains suspended, giving researchers precious seconds, a vastly longer window, to observe its quantum secrets. CAL cools clouds of rubidium and potassium atoms down to 100 billionths of a degree above absolute zero, making it, by any current measure, the coldest known spot in the universe. The cooling dance. Lasers, magnets, and vacuums. Achieving this cold is an orchestrated process requiring extreme control over light and containment. Vacuum chamber. First, the atoms are isolated inside an ultra-high vacuum chamber. This is crucial, as any stray air molecule would transfer heat and ruin the experiment instantly. Laser cooling. Scientists blast the atoms with multiple opposing lasers. These lasers are tuned precisely to the frequency of the atom's motion. Each photon collision saps a tiny bit of momentum, effectively using light as a brake. This technique, called Doppler cooling, gets the temperature down to about a millionth of a Kelvin. Magnetic trapping. The atoms are then confined by an invisible magnetic bowl. Powerful, fluctuating magnetic fields prevent the now sluggish atoms from colliding with the container walls, which would add heat. Evaporative cooling. Finally, they use a process similar to how sweating cools your body. Researchers strategically lower the walls of the magnetic trap, allowing the most energetic or hottest atoms to escape. This lowers the average energy and the temperature of the cloud that remains, achieving the final, record-breaking temperatures. The microgravity environment of the ISS allows this process to create and sustain the quantum phenomena for record durations. Record-breaking cold on Earth and new frontiers. The deep freeze milestones. Even on Earth, the cold atom race continues. Before CAL launched, MIT's lab had pushed temperatures to 500 picokelvin, that is 0.905 Kelvin above absolute zero. More recently, a German research team in 2021 dropped a chamber of rubidium atoms from a tall tower and achieved 38 picokelvin, setting the record for the lowest man-made temperature ever. They exploited the free fall time inside the tower to maximize the cooling duration, briefly mimicking microgravity. Exploring exotic phases. These experiments aren't just about BECs. By using different atoms like fermionic potassium, scientists create Fermi gases. When cooled, these gases form unique pairings that lead to different quantum states. By manipulating these fermionic and bosonic quantum states, researchers explore exotic phases of matter that are key to high-temperature superconductivity. Understanding how matter pairs up at these cold extremes might reveal the secret to making materials that superconduct at room temperature. A technological dream. Quantum phase transitions. Scientists can watch, in slow motion, as matter transforms from one state to another, providing insights into fundamental physics similar to how water changes to ice, but on an atomic quantum scale. The ultimate payoffs of ultra-cold physics. Ultra-cold experiments are already revealing insights into some of physics' biggest mysteries and promising world-changing technology. Bridging relativity and quantum mechanics. One of the grand challenges in physics is reconciling general relativity, the physics of the very large, like black holes, with quantum mechanics, the physics of the very small, like atoms. Ultra-cold labs provide a bridge. Black hole analogs. Researchers can create acoustic black holes within the BEC. Sound waves play the role of light, and they create a point from which sound cannot escape, an event horizon. Studying the sound waves near this horizon gives clues to Hawking radiation. Dark matter and gravity. Ultra-cold atoms are extremely sensitive to minute gravitational changes. Using this sensitivity, cold atom experiments are being used to search for elusive particles like dark matter and to test subtle variations in the force of gravity itself. Technological revolution. The practical applications emerging from this fundamental research are staggering. Quantum computing. BECs are essential for building qubits, the basic building blocks of quantum computers, and helping develop the most stable quantum memory. Precision sensing. The supercooled atoms, which are so sensitive to gravity, are used to create hyper-accurate atomic clocks and advanced inertial sensors. These devices are so precise they could one day replace satellite-based GPS by mapping gravity fields directly beneath the sensor. Recreating the Big Bang. Perhaps most profoundly, by cooling atoms to a crawl, scientists are, in a way, recreating conditions that existed mere seconds after the Big Bang, when the entire universe was once a dense, supercooled quantum soup. The ultra-cold lab serves as a kind of reverse time machine, allowing us to study the very first moments of creation. Out there, between the galaxies, space hangs at -270 degrees Celsius. But in a laboratory, floating in orbit, controlled by lasers and magnetic fields, we've gone colder still. We've mastered the art of atomic stillness. In those few billionths of a degree above nothingness, the universe whispers its secrets. How matter behaves when time slows, how energy flickers between being and not being, and how reality itself is stitched together. The coldest place in the universe is not a black void, it's a quantum laboratory. And that is a truly awesome thought. If this journey into the coldest corner of existence froze your mind, hit that like button and subscribe to Cosmic Crunch, where we explore the strangest, coolest, and most beautiful mysteries in the universe. Drop a comment. Would you dare step inside the coldest lab ever built? And stay tuned. Next time, we're turning up the heat with a black hole that's devouring an entire star.